Let us now address the issue of gravitational microlensing. This is lensing of stars by other stars. As you may recall, one possibility for the constituents of baryonic dark matter, or maybe all of the dark matter, was that they're in form of some underluminous substellar objects, which could be brown dwarfs or planets or even little black holes or neutron stars. And gravitational microlensing offered a way to test that. So if any such object passes along the line of sight to some background star, it will cause gravitational magnification. And there will be first rise in brightness as it approaches the critical radius, and then it will dim. So it'll be a symmetric light curve. It will also be same at all wavelengths because gravitational lensing is achromatic. How often will this happen depends obviously on cross-section, and cross-sections for stars are very small. Their diameters are very small compared to interstellar distances. So in principle, for any given star, it will be extremely rare. And therefore, you'd have to monitor a large number of stars in order to be able to catch one of these. Here are some of the modeled light curves for microlensing events. The peak magnification will depend on how well aligned the passage is. The closer, the better, of course. And how long does the event last will depend on the velocity of the lens relative to the line of sight. Faster moving ones will cause shorter events, obviously. In order to make this practical, one had to monitor many millions of stars. And one good solution was to look towards the Large Magellanic Cloud, which is about 50 kiloparsecs away, where many, many stars can be in the same field of view, and then monitor for a while looking for such events. This was done by a team called MACHO for Massive Compact Halo Object, and also another team called OGLE, and since then many others. So if the probability of seeing lensing happen to any given star is about 1 part in 10 million per year, then you better look at tens of millions of stars. Another possible direction is towards the galactic bulge, where a large number of galactic stars will be seen. So MACHO and OGLE were just the two experiments that started the whole thing. MACHO monitored almost 12 million stars for several years, and OGLE continues to monitor about 33 million stars. Many others have been started since then, and now this is a really well-established field. Shown here on the right is the first MACHO event detected in microlensing, and the two panels show a light curve in two different filters. This was an important discriminator against variable stars, because variable stars will tend to vary differently in different filters, whereas gravitational lensing is unique in the sense that it will work exactly the same for all wavelengths. And on the left, we see many more different events. To date, there have been probably thousands and thousands of microlensing discovered by different groups. Recall that Einstein radius essentially defines the cross-section for strong lensing. And in this case, it'll be the critical impact parameter for lens passing along the line, or close to the line of sight. Because mass of the lens enters under square root in Einstein radius, and the area of the cross-section is the square of that, it will be directly proportional to the mass of the lens. Thus, we can have an insight into the masses of the lenses, and if we look at the whole population of stars, then we can just add them up. So the net total fraction of all stars that are being lensed per unit time is giving you effectively an optical depth due to gravitational microlensing. The velocities of lenses are indicative of the velocity dispersion of their population, say halo, but they do not by themselves say anything about lenses. And also, the amplification says exactly nothing about any given lens. Now, since there are distances involved in the expression of the Einstein radius, we have to know where the lenses are. And so the interpretation of the result depends critically on where do you assume the lensing is happening. Are there stars near us? Are there stars in the Magellanic Cloud? Or somewhere in between, like in a galactic halo? If you know or assume somehow velocities of the lenses, say we know that the velocity of dispersion of halo stars is a couple hundred kilometers per second, then you can infer masses of lenses from the durations of the events. And typically, those are measured in days or tens of days. The shorter the event, the smaller the mass. So for an individual event, there are only two things we measure. We measure duration and the amplitude. The amplitude is simply telling you how well aligned you are. It doesn't say anything about lenses. The duration tells you about either the velocity dispersion or the individual masses. And the total number of lenses you see is telling you something about their density. So here are the original matcher results. They're expressed in probability contours as a function of the lens mass and a fraction of the mass of the galactic halo that could be attributed to them, assuming they really are in the galactic halo. The surprising result here was that typical mass was supposed to be about half solar mass. This was unexpected because the only thing that could be like that would be white dwarfs, which are evolutionary remnants of more massive stars. But that means that there must have been some huge population of progenitors of those with other consequences which are not seen. And so most likely, the solution of this is that lenses were actually not in a galactic halo. They were either in our disk of our galaxy or Magellan clouds themselves. But even if they were in a galactic halo, the sheer frequency of them eliminated the possibility that all of the dark matter is in form of machos, regardless of what the machos are, brown dwarfs or black holes or anything else. This was still a very powerful result. Sometimes you can find where the lens is. One is if it's sufficiently close by that you can use parallax, and the other one is if there is a binary, because then you can use geometry of the binary star to infer how far it was. A more recent twist on this is that this kind of measurement is used to discover planets around other stars, a complementary method to those seen by, say, Kepler satellite that uses eclipses or kinematical measurements with radial velocities. Next time, we will talk about dark energy, probably the single most understanding problem of physical cosmology today.